All right, so we kind of hinted at the fact that there could be some other zeros. Not all of our solutions are going to be real. So what do these other solutions look like? Well, review the number system. We're used to talking about real numbers, but then there's also imaginary numbers, right? And imaginary and real numbers, or we'll put the little I, where real numbers and imaginary numbers overlap, we call that what? They're complex numbers. Okay? Complex numbers look like a plus bi, where both a and b are real, but I represents the imaginary number, the square root of -1. Okay? So that's where the rest of our solutions are going to be. If in any of these polynomials, let's say we had a 4th degree polynomial, in a second we're going to say that there really are 4 zeros, then if they're not real, they have to be complex. Okay, a plus bi. So a couple of theorems: fundamental theorem of algebra and the factorization theorem for polynomials. In a complex number system, every nth degree polynomial equation has exactly n roots, and every nth degree polynomial can be factored into exactly n linear factors. So if we have a cubic kind of problem, we can find 3 linear factors. Okay, if it's 4th degree, we can find exactly 4 linear factors. All right, the number of zeros theorem: any polynomial of degree n has exactly n zeros, provided a zero of multiplicity k is counted k times. So this only says that if we've got x minus 2 times x minus 2, we count each of those once. That would be 2 different zeros. And we've talked a little bit about multiplicity already. Okay? In short, it doesn't mean that there's n unique zeros. Some of those zeros are repeated. Okay? So how are we going to find these zeros? Well, just kind of a review. It says find all solutions of the equation in the complex number system. Okay, this is something we should be comfortable with already. I can solve this one, this first one, by extracting square roots. Okay, we're just going to say x minus 2 squared equals -9. Then what can I do? Take the square root of both sides. So that's plus minus the square root of -9. Okay. And of course the square root of -9 is going to be what? What is it? 3i. Plus minus 3i. Okay. And so there are 2 solutions. X equals 2 plus 3i and x equals 2 minus 3i. Okay, and we had a 2nd degree polynomial. Okay, if I have x cubed equals -8, we talked about this in class the other day too, didn't we? Or was that another class? This factors as x minus 2 times x squared plus 2x plus 4. Okay, this is our pattern for difference of cubes. All right, and so obviously we get what as a 0 here? 2. Okay, but for this piece, this isn't going to factor, and so we'll have to use quadratic formula to get to our solutions. Okay, so we can say x equals minus b, so minus 2 plus or minus the square root of b squared minus 4 times a times c all over 2a. Okay, and so we get minus 2 plus minus the square root 4 minus 16 is -12 over 2. Okay, what's the square root of -12? Do you all not know, or you just don't want to tell me? Do y'all know what it is? No, you don't. Okay, well, y'all got to say so. We have no clue. So I'll know. Okay, if we're talking about the square root of negative 12, we can distribute radicals over a product and also over a quotient. So what I'm going to do, since we're talking about square roots, is try to break this thing up into perfect squares. So square root of negative 12, I could rewrite as the square root of 3 times 4. 4 is a perfect square, times negative 1. Or if we write it all out, square root of 3 times square root of 4 times the square root of negative 1. Well, the square root of 4 is what? 2. The square root of negative 1 is I. And then we're left with root 3. So it's 2 minus 2 plus minus 2i root 3 all over 2. I can distribute that 2 that's in my denominator. So we get minus 1 plus minus I root 3. And so that's the other two solutions.
I don't understand how the difference in squares you got what you got and minus 2 plus or minus the square root of
Okay, right here, this piece.
yeah, right.
Oh, this is just the quadratic formula. So remember the quadratic formula, x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so in this case, a is 1, b is 2, and c was 4. Okay, you want to keep that in mind, the quadratic formula always. It pops up again and again. Okay, other questions? All right, excellent. So possibly, without having to go through everything we've been talking about, we could do some factoring, use the quadratic formula. That'll help us find all of our solutions. Okay. We have here what's called the conjugate pairs theorem. And basically what that theorem tells us is that, everybody got this? Right here? Yes, because that was the pattern for difference of cubes. So the pattern is if we have a cubed minus b cubed, okay, which I notice I've got a perfect cube here and I've got a perfect cube here. It's 2 cubed. So one of the patterns that you learned some time ago was a minus b times, we get a squared, we get b squared. In the middle, we just multiply a and b, and the sign changes, plus ab. And so I took my a and squared it. I took my b and squared it, and in the middle, it was a times b. But I changed the sign.
Okay, so that only worked because
Right, for perfect cubes. If it had been plus, then it almost works the same way. We get a plus b times a squared minus ab plus b squared. Okay, that's our factoring pattern for perfect cubes. Okay, and now fair game for the test. Okay. All right, so the conjugate pairs theorem. Basically, it says if p of x is a polynomial function whose coefficients are real numbers, and if z equals a plus bi is a 0 of p, then the conjugate z equals a minus bi is also a 0 of p. Okay, and we saw that just in this last example. Okay, basically this says if we get minus 1 plus I root 3 as a 0, then minus 1 minus I root 3 has to be a 0 as well. Okay, they both have to be zeros. They're conjugate pairs. What's so special about that? Well, go back the other way. In general, we're talking about A minus B, A plus B. And when we multiply those things out, we get A squared minus B squared. Well, usually in there's some undesirable thing like an imaginary number. Okay? And so when I multiply that complex number by its conjugate, the imaginary number goes away. All right? We do it the same thing with radicals. Remember when you were rationalizing radicals that had, rationalizing expressions that had radicals in the denominator. Remember doing that? Okay? We multiplied top and bottom by the conjugate. We might have had something like 7 over 2 plus root 5. Well, we didn't just leave that like that. We had to say times 2 minus root 5 over 2 minus root 5. Okay? When I multiply the bottom, this becomes 4 minus 5. Okay? Because I had conjugate pairs, and this principle applies there. Okay? So what we're dealing with is the imaginary numbers. And we'll come back and talk about that in a minute. Okay, odd degree polynomials with real zeros. Any polynomial p of x of odd degree with real coefficients must have at least one real zero. Why do you think they said that? Suppose we have a polynomial of degree 3. Why is it that it would have to have at least one real zero? Well, that's what it's saying, but if let me ask you this question. If the zeros aren't real, they have to be what? Or complex, right? Because it has a real part and an imaginary part, so we call it complex. But if we got one complex zero, then we have to have what? 2. They have to come in pairs. That's what the conjugate pairs theorem tells us. So if I had 3 zeros altogether and 2 of them are complex, the other one has to be what? Real. You have to have at least one real zero when we have an odd degree. So keep that in mind. Okay? So how does this all play together? It says find the remaining zeros of a polynomial p of x with real coefficients and with the specified degree and zeros. Okay, so I've got a polynomial of degree 3. Its zeros are 2 and 2 minus I. Microsoft Word tried to be smarter than me. That's a lowercase I. Okay, 2 and 2 minus I. So how many other zeros are we looking for? 1. Okay, we already have 2. The degree is 3. We need one more. What must that one be? 2 plus I. Okay, it has to be the conjugate pair. All right, we got degree 6, and some of the zeros are 2i, 4 plus I, and I minus 1. So what are my other zeros? Mm-hmm. Very good. All right, very good. Okay, questions about this? Those are the conjugates of the ones that we have. We had positive 2i, so minus 2i had to be a 0. We had 4 plus I, so 4 minus I had to be a 0. Okay? The one sign, that's it. In general, although I'm looking at this 4 plus I and I minus 1, that one might provide a little bit of a problem for us. Because generally, we write these as A plus BI. The imaginary number comes second. So this is really I plus 4. And so the conjugate really should be I minus 4. I'm sorry. Did I do that right?
No, mine is the A plus B.
Let's see. Hold on.
It would be the I minus 1 would be negative 1.
Yes, this would be minus 1 minus I, or rather plus I. And so the conjugate would be minus 1 minus I. Okay, that's the conjugate. Okay, questions about that? Okay. All right, very good. All right, find the polynomial p of x with real coefficients having the specified degree, leading coefficient, and 0. So this time we're going backwards. They want us to actually come up with the polynomial. Okay, so it's degree 4. It has a leading coefficient of negative 3. We've got zeros of 2 plus 3i and 1 minus 4i. Okay, so my other zeros are going to be what? Okay, very good. So my polynomial then would look like p of x equals, if these were real numbers, if I told you that x equals 2 is a 0, then the factor would be what? X minus 2, right? That would be the factor. So if 2 plus 3i is a 0, then x minus 2 plus 3i is a factor. Okay, and then we're going to have x minus 2 minus 3i is a factor. Everybody following? Okay. Well, they ask us to find the polynomial. So we're trying to find the polynomial function that has these things as a 0. Okay, so we're kind of working just right. That's exactly right. Okay, if we said, like she was saying, x equals 2, that implies that x minus 2 is a factor. And so here we have x equals 2 plus 3i. So x minus 2 plus 3i is a factor. Okay, x minus 2 minus 3i is a factor. And we have x minus 1 minus 4i, and then x minus 1 plus 4i. And they told us that it had a leading coefficient of negative 3, so we can just put him out front, negative 3. Okay. Now what we would like to be able to do is clean this up. That doesn't look like a polynomial to us. That's not how we get them. So how do we make that look more like the polynomials that we're used to seeing? We're going to manipulate this just a little bit. Okay. Right here, I'm going to distribute the minus. We get x minus 2 minus 3i. Okay. And it's okay if I drop this here. It doesn't change a thing. Is that right? Everybody okay? All right, because we're not, there would be a minus there, and there's still a minus there. Same thing here. X minus 2, except now when I distribute, this becomes plus 3i. Okay, and I'm going to stop and tell you why I'm doing this. Notice here, now I've got the same thing here and the same thing here. These are now, these factors are conjugate pairs. Do you see that? And so when I get ready to multiply these two together, they factor, or they multiply out to be x minus 2 squared minus 9i squared. Okay, because of the rule that we talked about just a little bit earlier, a minus b times a plus b equals a squared minus b squared. So x minus 2 is my a, And then the 3 i's, those are going to be my b's. All right, and so when I multiplied them together, I got a squared minus b squared. Okay, and we'll go one more line to simplify it just a little bit, but I wanted to show you that before we got too much farther. Same thing here. We get x minus 1 plus 4i, and then x minus 1 minus 4i. And so that multiplies out to be x minus 1 squared minus 16i squared. Okay. Everybody okay with that? All right, so if we clean that up just a little bit, this is negative 3. X minus 2 squared is what? X squared minus 4x plus 4 minus 9i squared is what? Well, no. What's 9i squared? It's just what? It'll become plus 9. I squared is negative 1. Negative 1 times 9 is negative 9. We already had a minus here, so it's plus 9. Okay, and then we get x squared minus 2x plus 1 plus 16. Okay, we're getting really close now. 9 and 4 is plus 13. And x squared minus 2x plus 17. We're trying to get a single polynomial. Okay, so the last thing we have to do is actually multiply those two together. Well, 3 together. 1, 2, 3. And then we have our polynomial. Okay?
So for the line one line you just factored, I mean, you went and did x minus 2 and then x minus 2 and then...
That's it. Okay. All right, so I'm going to go ahead and multiply these together. All right, we got negative 3. I'll just let him sit on the side. If I distribute x squared, then that's going to be x to the 4th minus 2x cubed plus 17x squared. If I take minus 4x, we get minus 4x cubed. Okay, I'm distributing him to each one here. Plus 8x squared. 4 and 17 is 68, so that's minus 68x. And then finally distribute 13 plus 13x squared minus 26x. And 13 times 17 is... I got 221. Is that right? Okay. Plus 221. Okay. Combine the like terms and multiply by negative 3 and we'll be done. Okay, so we get negative 3, x to the 4th. For my cubes, I'm just marking these out for my reference. Minus 6x cubed. Okay. 17, we get 25x squared plus 13 is 38x squared. And then minus 94x plus 22. And then multiply that by negative 3 and we are done. (114) minus 114 x squared plus I got 282 x minus 66. And that's it. That was a good bit of work, but you had to just persevere. Questions about that? Let's talk about what happened, because it's going to happen or need to happen again. Okay? So they wanted us to come up with the polynomial, all right, given the zeros and the leading coefficient. They gave us, well, some of the zeros. So the first thing we did was we found the remaining zeros. Then we wrote those zeros as linear factors. Okay, questions about that? Okay. All right, then we had to, this little step is the key to making this work. So we distributed that minus and kind of regrouped things so that we had conjugate pairs. Because the way that these are written right here, they're not conjugate pairs. Right? We had x minus 2 plus 3i and x minus 2 minus 3i. Those are not conjugate pairs. But once I distribute it, then yes, these are conjugate pairs. And that helped make it easy for me to multiply these together. And if you don't believe that that was easy, then try doing it without rewriting it as conjugate pairs. And we would still be trying to get to the answer. And so use that. Went on and expanded these things. And then finally came to our answer. Questions about this? Can you do this? Okay, I got some slight... Possibly, okay. All right, we're going to need to be able to do this. Let's see if we can set up this next one. I don't know if we'll finish it, but we'll try. It's not going away. Sure. Alrighty, let's then look again at the next one. Okay, we got degree 6. Wow, that's a lot of them. But we got something interesting that's going to make it a little easy for us. And that is we got a 0 that has multiplicity 3. Okay, how do you think that's going to play into our polynomial? Okay, so how would that show up in the polynomial? Just x cubed, right? P of x equals x cubed. If we had that and set it equal to 0, we get x equals 0, and we get it 3 times, okay? Because of the power 3. So that's half of them already done, okay? We also have a 0 of 3, so that factor is going to be what? Okay, x minus 3. Okay, we have 2 minus 3i, so that factor is... Very good. Nope, minus, because the 0 is what? Right. Very good. Okay, so we've got it set up. All right. Okay. We got x cubed, and if we want to, we can go ahead and multiply these two together. X cubed times x is x to the 4th minus 3x cubed. Okay, got that part multiplied out. And then here we're going to use our regrouping trick. So this becomes x minus 2 minus 3i and x, I'm sorry, that'll be plus 3i. And then x minus 2, this one is minus 3i. Okay, once we distribute that minus sign. Okay. And oh, let's not forget our leading coefficient of 4. And we can go ahead and call that 4x to the 4th minus 12x cubed if we want. Okay, so when I multiply these together, we get x minus 2 squared minus 9i squared. Okay, and 9i squared is, okay, by the time we distribute this minus with it, it's a 9. So this is 4x to the fourth minus 12x cubed times x squared minus 4x plus 4. Is this the exact one we had before, that factor? Seems like it. Plus 9. Okay. Or we could call that plus 13. Okay, and then we have to go on and multiply those two together. Still not as bad as the last one. 4x to the fourth, I'm going to distribute that. I'll get 4x to the sixth minus 16x to the fifth plus 52x to the fourth. Okay, then I'm going to distribute the negative 12x cubed. So we get minus 12x to the fifth plus 48x to the fourth minus 13 times 12 is 156. 156x cubed. Okay, then combine those like terms. I've got 4x to the sixth minus 28x to the fifth plus 100x to the fourth plus 156x cubed. And so that's our polynomial. All right, questions? All right. Minus. Yes, thank you. All right, excellent. Go try this. The only way to learn how to do these things is to practice, practice, practice.